For your AI and hardware-accelerated workloads, Palette has you covered with curated profiles that make the deployment of these clusters and applications simple and repeatable. In a non-Palette deployment, getting the GPU configuration settings requires an understanding of the GPU operator configuration. The configuration settings can be quite involved, as there are dozens of parameters that are commonly configured to set up the operator. With the GPU Operator pack in Palette, we can quickly deploy the NVIDIA GPU Operator into our clusters without any of the guesswork. IT teams now have the ability to deploy GPU-accelerated clusters for their AI applications faster and with more consistency, even across hundreds of clusters. Let's take a look at how that happens. In Palette, we start by selecting our GPU Operator profile that we pre-configured for this demo. This profile is for deploying a Kubernetes cluster on AWS. We give the cluster a name and select our cloud account that has the permissions to create the required resources. Here we can see the GPU Operator pack configured in the profile. Through pack presets, we can allow for easy configuration based on the environment being deployed to. In this case, we are keeping the defaults as they match our deployment type. We will add an ingress component and a sample computer vision application to demonstrate the end-to-end deployment. Next, we select a cloud region, provide an SSH key pair, and enable static placement to deploy our cluster to an existing VPC. We then select an instance type and subnets for our control plane nodes. In this case, we are using a T3A2xlarge and 2 availability zones. We do the same for our worker nodes. Since we are enabling the NVIDIA GPU Operator, we will use G5.2xlarge nodes as they have our GPU hardware for acceleration. We also select the private subnet for each availability zone. As part of the options in Palette, we simplify Day 2 operations, such as OS patching. By default, this is enabled. For the purposes of this demo, we're disabling it. Everything looks good. Let's click Finish and watch the cluster deploy. As the build happens, we can see the profile layers going green as components are successfully installed. The GPU Operator and sample application are the last components installed based on the order defined in the cluster profile. Once all the layers are green, the cluster is in the running state. Let's take a look at how our application is working. As we can see, our computer vision application is up and analyzing and classifying objects. Powering intelligent applications at scale takes more than just smart code. It takes smart infrastructure. That's where NVIDIA's BlueField-3 DPUs come in. The NVIDIA BlueField DPU, also called Smart NICs, is able to provide fast connectivity up to 200 gigabits a second. They can offload Kubernetes pod networking overhead onto the hardware, thereby accelerating application workloads. There is one catch, though, and that is correctly building the infrastructure and the Kubernetes cluster with the required software stack this time and every time. NVIDIA provides a guide for us. The best one is the Reference Deployment Guide, which you can find on their website. But there is one catch. It is 105 pages long. Some of that you will use to set up the required network infrastructure, such as setting up BGP, but after that, there are many pages of steps for deploying the actual cluster. We have replaced all of those steps with a single cluster profile for Spectro Cloud Palette that is straightforward to deploy with no more hassle. The physical environment we are using looks like this. We have 2 bare metal servers, each with one NVIDIA BlueField installed and connected through a 40 gigabit link with a Cisco Nexus leaf switch. Elsewhere in the data center, we are going to use a VM as the control plane node. The leaf and spine switches are running BGP so that the network can learn routes advertised by the DPUs and allow the other VLANs in the network to reach those endpoints. The first step is deploying and registering all 3 servers with Spectro Cloud Palette. Here we are using agent mode so that we can deploy any operating system we choose, and just install a Palette agent to be able to turn them into a Kubernetes cluster later. We're deploying the VM that will become the control plane node using Ubuntu commands to automate the process. Once the node is up and running, it will self-register with Palette and show up in the list of available hosts. With all the hosts registered, now we can deploy a DPU cluster. We select the cluster profile we made for this and follow the wizard. In the Profile Config step, it allows us to adjust the handful of variables that tailor this cluster to our specific deployment environment. These defaults are already in line with our environment, so we will accept the defaults and move forward. Then we configure a time server, the IP address that the Kubernetes API server will listen on, and we select our control plane node for deployments. For DPU clusters, we first need to deploy the control plane only, and then add the worker nodes in 2 remaining steps afterwards. The configuration looks like what we want. Now let's kick off the deployment. As the cluster builds, we can see components getting automatically installed with profile layers going green step by step. The DPU services are already getting pre-staged as one of the last steps in the cluster profile. Once all the layers are green, the cluster reaches the running state and has completed provisioning. Now we will bring in the worker nodes. The first step is to go back to the cluster profile variables and enable the setting that can only be enabled after the control plane has been fully built. This is because we only want the DPU resource injection to happen on the worker nodes, not on any of the control plane nodes. Once enabled, we can go into the Nodes tab, add a new worker pool, and select the 2 nodes with DPUs in them. After a short wait for Spectro Cloud Palette to provision Kubernetes on these nodes, they have been brought into the cluster. When the worker does join the cluster, the DPUs are automatically detected and flashed with the desired image. The server then reboots so that the DPU can get initialized to offload pod networking to the DPU hardware. This process takes 10 to 20 minutes to complete. And once everything is up and running, our cluster is ready for accelerating applications. All right, let's add a simple example application to demonstrate the acceleration. We'll use an add-on profile that installs the iPerf3 testing tool with the server running on worker 1 and the client running on worker 2. We apply this add-on profile to the cluster and wait for the new parts to show up. As you can see, they get scheduled onto the workers as expected. We'll then copy the pod IP address of the server pods and start a shell into the client pod. Then we tell the client to run a speed test against the server IP. A few moments and here's our test results. Performance is only limited by the link speed, so only 40 gig in this case. You'll see closer to 80 plus gigabits per second with 100 gig link speed, for example. We can also find the IP address assigned to each DPU and connect it to open the Blueman Web GUI, giving you even more information about the DPU, its health, and live metrics information.